Okay, next we will see different type of the matching network. So in this class we are not looking at back or disjunct matching because this is have been covered in microwave classes during undergraduate or during your master program. So for this one we will look at the quarter wave transformer for the first one. So this is a single section quarter transformer. Why? What we can see here, this is our antenna. So we name this is antenna. So this is quarter wave transformer. Why we call it quarter wave transformer? Because it have a lambda over 4. So the length of this section is lambda over 4, and the impedance of this section is equivalent to Z1. And we want to match from this antenna to the Z0 is our system. And take note that we need to place our antenna here, which is at the S0 distance from here, from our impedance from our antenna. We place this transformer at impedance of the Rin, where Rin should be equivalent to real impedance. I mean is that A plus J 0.0. And this is how we have seen also in microwave classes. So what we want to see here now, we want to see these sections, this multi-section transformer, because single section only cover the single narrow band. But in order for we have seen some of the case of the application are broadband. So that's why we need to have the multi-section. So this can cover the broadband applications. So for the broadband application, what we can see here, this is still we assume as an antenna, and this is our Z0 is a system. So we will have Z1, this is the first section, Z2, second section, Z3, Z4 until Zn is the end sections. So for every section, the length must be equivalent to lambda over 4. Every section, the length is lambda over 4. And take note that again, these places at these locations, our impedance should be Rin equivalent to A plus J 0.0. Okay, so first how we want to see is that because we can see here from this Z0 at this section as this stage, we can see that our impedance at the left hand side is Z0, the right hand side is Z1. So this first stage we use a rho 0. Rho 0 means that the reflection coefficient at 0 sections. So we'll see after this what is the equivalent equation that we can use over here. For the rho 1 means that is a stage 2. For the stage 2, our left impedance is Z1, our right impedance Z1. So this is a rho 1. And for the rho 2 means that the stage 3, the left impedance is Z1, the next impedance, right impedance should be Z3, and the rest. So we can see that if rho n meaning that you have Zn, and the next impedance side, the next impedance section is Zn plus 1. So this should be, in order we want to use the quarter transformer, we must make sure that the impedance as this position location where we attach the transformer must be the real impedance. So this is another application that we use a lot in the microwave technology. So where we use the power divider. So if you have so much power divider being used, T-junction power divider used, sometimes we call it also corporate feeds. So for the single section transformer, our impedance must be real, as I mentioned just now, meaning that our Rin must be real, meaning that you must make sure that Rin equivalent A plus J 0.0. So we can design this to get Rin 0.0. And then the transformer impedance is equivalent to Z1. How we get the transformer impedance? So Rin multiplied Z0 and square root of these two. So for the quarter wave transformer multi-section, so it's basically it's less sensitive, so that they can have the frequency variation broader, so we can have the broader bandwidth matching. Where we have multi-sections quarter transformer and the load impedance, again we have to make sure it's a real. So this is the reflection coefficient where can we see that's the rho 0 plus rho 1 and so on, so that we can have these summations cumulative. Basically, row n, as I mentioned just now, at any stage 1 or stage 2 to stage 3. So at the stage 1, so this will become 0. At stage 2, it become 1. At stage 3, it become 2. So for example, you're looking for the stage 1, meaning that a row 0 is a z naught minus, z1 minus z naught equals z1 plus z naught, the impedance of stage 1. At stage 2, row 1 is zn plus z1 plus 1 means z2 minus z1, z2 plus z1. So to get the reflection coefficient. And this is where we can find the fractional bandwidth. Okay. So this is where we okay, the other thing is that if you have the RL less than Z0, so meaning that you will have the negative reflection coefficient. So negative sign, don't forget to be used over there. If you forgot to use minus sign over here, you will get a different answer of the load. Okay, so for the binomial design, we will use this the quite powerful formula where we equivalent at any position of reflection coefficient, we can find their reflection coefficient stage, which is 2 minus n, stage of n, RL, the load impedance, minus Z0, characteristic impedance, and this is binomial, C n to n stage, e to the power 2n theta. So what is that? So in theta basically is a binomial, so we can use n start from 0 to 1 to n1, and rho n equivalent to 2 minus n RL Z0 over. So at any position of stage, we can find this n. And our fractional bandwidth, so we can see the important thing to find over here is we need to identify at the maximum frequency or at the maximum reflection coefficient. So if you have row 1, row 2, row 3, so which one the maximum value? So that's maximum value will be used over here. The rest are using the M standard or understood impedance value. So basically, this is the procedure. We identify the load impedance, we identify the input impedance, we need to identify the number of section. Remember, every section is a Z1 lambda is over 4. And then we need to find the characteristic impedance of each section, and then at the end we need to find the fractional bandwidth. So this is another design method. We can use Chebyshev, or so when Chebyshev, this is the reflection coefficient that we can use over here. So that's all.